Hello and welcome to a lesson on the fundamentals of probability. So we've talked about in the last three topics some different ways that we could find the total number of outcomes in a situation. We talked about finding those outcomes using the counting principle, using combinations, using permutations, and all of those are going to be helpful in the next phase of our module, which is probability. So what is probability? Probability is the likelihood of something occurring. Okay, so if I said, what's the probability that, I roll a die, it's got 6 sides, what's the probability that I land on a 2, we can make a calculation for that. We could say how likely it is that we would roll a 2. Okay, so probability is the likelihood, or the chances, if you like that word better, of an event occurring. And the notation for the probability of some event, let's just say event A occurring, is written like this. The probability of event A would look like that notation-wise. It could be the probability of B or C or whatever event we have in there, or it could be the probability of rolling a 2 on the die, or the probability of picking a king from a deck of cards. So whatever it is we're trying to choose is going to go inside of the parentheses there, and then the P represents the word probability. Okay, so that's notation. Now when we're trying to find the probability of an event occurring, we have to know the total number of possibilities in that situation. And that's why we spent those 3 sections talking about ways to find the total number of outcomes or possibilities. So that total number of possibilities make up what we call, and what we used in our previous module, we call the universal set. Okay, the universal set, and we're going to call that U, and it's written with the notation N of U. Okay, so the total number of possibilities or outcomes in an event make up the universal set. The universal set is U. The number of outcomes in that universal set is N of U, and we saw that in our first unit as well. That's the number of elements in the set, or the cardinal number for the set. That's what that little N in parentheses means. Okay? Now probability can be written a few different ways. We typically see it as a fraction, but that's not the requirement, the only way we can write it. So it can be written as a fraction. Fractions can also be converted nicely to decimals, and then decimals can be converted to percents. So we can write probabilities in all 3 of those ways. And I don't think one is preferred over another, but generally if you're dealing with a situation where you end up with a fraction for your answer, just make sure your fraction is reduced. There's no point in converting it. Now, if you're dealing with decimals in your problem, then maybe having a decimal answer makes sense. Or if you're dealing with percentages in your problem, then maybe using a percent makes sense. So they're all acceptable, and converting for the purpose of converting is kind of silly. So I would say, leave it in the form that is asked or required or given in your problem. Okay, but you should be able to convert. So let's say that for this example here, the probability of some event A occurring is 2 out of 8. Well, 2 out of 8 reduces, and if you don't like reducing fractions, then use Desmos. Okay, use your calculator. If you put in 2 divided by 8 into your calculator, it's going to give you the decimal, which is helpful. But if you hit the little fraction over here in the blue, it will also reduce your fraction for you. So as a reduced fraction, we'd say it's 1 out of 4. And let me go back to hit the fraction again. It'll take me back to my decimal form. So I know as a decimal, it's 0.25. And then do you know how to take the decimal and make it a percent? Well, 0.25 or whatever your decimal is, if you multiply by 100, it's 25%. You're basically moving the decimal 2 times. If you move the decimal 2 times this way, that would be to the right, you're going to see what the percentage is. Or you could multiply by 100 to see that it's 25%. Okay, so this is 25%. So all of those would be equivalent ways to state the probability for event A. All right? Now, some things we should know about probabilities, other things we should know, I should say, that your probability has to be a value from 0 to 1. 0 being the smallest probability that's possible, and 1 being the largest probability that's possible. Or you could also say 0 being 0%, 1 being 100%. Right? You can't have a probability less than 0%, and you can't have a probability greater than 100%. And therefore we can't have probabilities that are between 0 and 1 if we're looking at the fraction or the decimal value. Okay? If we have the probability of event A being 0, what happens if the probability is 0? How could we describe a probability of how could we describe an event that has a probability of 0? Well, if the probability is 0, that means it's not going to happen. We would say that an event that has a probability of 0 is impossible. So it's impossible if the probability is 0. Okay? Well, I guess we could leave that there. What if we had a probability of 1? Let's go to the other end here. If the probability of our event is 1, that would be 100%. So this is a 100% chance that it's going to happen. Over here, probably 0% chance that it was going to happen. Okay, if it's 100% chance it's going to happen, 100% guaranteed to happen, we could say that this event is certain. Okay, what if we're in the middle? What if the probability of our event occurring is 0.5? If it's 0.5, that would be like a 50% chance. So 50% chance of happening means there's a 50% chance that it doesn't happen. So here we would say it's equally likely or unlikely. Equally likely or unlikely. And then if we're anywhere in between, so if we're in this area here in between 0 and 0.5, then we're going to say these events are less likely to occur. And then if we're in this region here, okay, anywhere from 0.5 to 1, we're going to say that events are more likely to occur. Let's see. Let's go with... Oh, that's terrible. I don't know if that's you. Can you read that? That's a tough one for me to read. Let's see. Let's go more like that's better. More likely to occur here. Okay, so probabilities, again, decimal, fraction, percent, all okay. Probabilities have to be from 0 to 1 or 0% to 100%, and ranging from impossible to certain, and then those descriptors in the middle. In general, how do we go about calculating a probability? Again, just to relate this back to what we were doing before with sets, the probability of event A occurring is going to be the number of elements in set A. So here's our notation for that. The number of elements in set A divided by the number of elements in the universal set. So that's the number of elements in the universal set. Okay? Now that might sound a little complicated or even look a little complicated, but again, I want to tie this back to what we were doing before. So let me deviate from this for a second. Let's just say that we had 100 pieces of fruit and 23 of them were apples. Okay? If we were going to make a Venn diagram for this situation, and let's say that this circle is apples, and then we have this universal set of fruit. Okay, 23 of the pieces of fruit are apples, which means the remaining 77 pieces of fruit are not apples, and they would be outside of the apple circle, but inside the universal set, right? If I said we were going to pick one piece of fruit from at random, and I wanted to know what would be the probability of choosing an apple, okay, then I would need to know how many apples are there, and I need to know how many fruits are there total, right? The total number of fruits to choose from is 100, and the number of apples there are in that bunch would be 23. So our probability would be 23 out of 100, okay? And again, this is just to try to help you see the notation. It's what's in the set that we're looking at, in this case apples, what's in the universal set, or the total number of options there are to choose from. That's all that notation means, okay? So let's go back here. Now, there are technically two types, well, there are probably more, but in general, you're going to see two types of probabilities. We have what we call empirical probability, and then we have what we call theoretical probability, okay? And what's the difference? Let me again show you here. Let's say that we wanted to know the probability that we get an A on, let's say, the next module quiz, okay? So think about this. What kind of quiz grades are going to be possible? Well, quiz grades range from 0% to 100%, right? So from 0 to 100%, that's technically 101 different scores that are possible. You with me? Okay, there's 101 different scores that are possible. So if you wanted to know the probability of getting an A, well, how many of those scores are A's? Well, you'd have a 90, a 91, a 92, a 93, 94, 95, 96, 97, 98, 99, and then of course the 100. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 of the scores are A's, and 101 scores are possible. So the probability of getting an A should be 11 out of 101. Theoretically. Theoretically, that is true. That's if earning every single grade was equally likely. But we know that it's not equally likely for people to earn A's as it is for other people to earn A. For one person to earn A as it is another. You know, some people struggle a little more with math. Some people math is a little bit easier. So theoretically speaking, you know, your probability should be, well, you have those 11 different grades out of the 101 possible grades. But maybe you've earned a C on the last 100 quizzes you've taken in your life. You're probably going to be more likely to earn a C than earn an A, right? Or maybe you've earned a B on the last 50 quizzes that you've taken. So when we calculate our probability, do we calculate the probability based on, in theory, what should happen? Or do we base it on our own particular results, right? Our own circumstances? Well, we can actually do both, and that's why we're going to distinguish between two types of probabilities, okay? So one of the types of probabilities is what we call empirical probability. Empirical probability is also called experimental probability. So experimental, because it's based on, oops, I can't write all of a sudden. Because this would be the type of probability that is based on an actual experiment or actual results. So if you actually showed the results of all your previous quiz scores from college, and you figured out how many of those were A's, you could maybe calculate the probability of earning an A again. All right. So the experimental or empirical probability is based on actual results. Okay, an actual experiment or actual results. So, for example, let's say a 6-sided die is rolled 20 times. In theory, when you roll the die, you have an equally likely chance of rolling a 1 or 2 or 3 or 4 or 5 or 6. So if we were to roll it, let's say 6 times, in theory, we could get a 1, a 2, a 3, a 4, a 5, a 6. But is that going to happen necessarily? No. Right? It could be that we roll this 6 times and we get a 5 every single time, right? So we could calculate our probability based on theory, or we could perform an actual experiment and base our probability on the experiment. So in this particular experiment, again, the die is rolled 20 times, and we landed on a 1 5 times, a 2 landed 4 times, a 3 landed 4 times, a 4 landed 3 times, a 5 landed 3 times, and a 6 only happened once. So it's not equal here, right? Based on this experiment, those things didn't happen an equal number of times. But that's okay. Excuse the door slam if you heard that in the background. I have a 9-year-old who just had to have a snack right now. Sorry. Okay, probability of landing on a 1. Well, in this scenario, we landed on a 1 5 times, and that was out of 20 times total. So we're going to say the probability of landing on a 1 was 5 times out of the 20 total. And 5 out of 20 would be an acceptable answer. Also, we could do the reduced fraction, which is 1/4. Or we could do the decimal, which is 0.25. Or we could do the percent, which is 25%. Okay, but I'm totally okay with whatever of those. If you're going to leave it as a fraction, make sure it's reduced, but any one of those answers would be fine. Okay? How about the probability of, let's see, rolling a 4, landing on a 4? Well, in this experiment, a 4 happened 3 times out of the 20. So 3 out of 20 times we landed on a 4, and 3 out of 20 doesn't reduce. But let me just show you. 3 out of 20 doesn't reduce, but we could make that a decimal of 0.5 if we wanted to, or 15%. Okay? How about the probability that we land on an even number? So evens would be 2, 4, 6, and we had that 4, 3, and 1 time. So 4 plus the 3 plus the 1 would be, let's see, 8 times total. oops, I did a plus and I don't want that there. 4 and 3 would be 7, 7 and 1 would make 8. So 8 times out of the 20 total rolls, we got an even number. So 8 out of 20, and again, 8 out of 20 we could reduce. We could make that 2/5, or we could leave it 0.4, and that would be 40%. So 2/5, we're good with that. How about the probability of rolling a 6? Well, a 6 happened 1 time out of the 20, so 1 out of 20 times we land on a 6. What about the probability of not landing on a 6? So letter E here is not a 6. Okay, not a 6 is the rest of these times, and we can go about calculating this 2 different ways. Not a 6 would be all these, right? Everything from 1 to 5 is not a 6. So I could add all that stuff together, or if 1 out of 20 times I did roll a 6, what happens the other 19 out of 20 times? I'm not rolling a 6, okay? The probability of something happening added to the probability of it not happening has to make up the total of what happens. It has to make 100%. Hopefully that makes a little sense, and we're going to see more of that. So if 1 out of 20 times we get a 6, that means the other 19 out of 20 we don't. Alright, what about the probability of rolling a 7? Well, this was a 6-sided die. There are no 7s, so this is a 0% chance, 0 out of 20 if we want the fraction, or just a 0 or 0%. How about that it's not a 7? Well, every single one of the numbers is not a 7, so all 20 out of 20, or 1, or 100% of the time, we are getting something that is not a 7. Now I just want to change this to red, sorry. This was 0 out of 20, which is just a 0. Okay? Hopefully that's not so bad. Now, I don't want to say it's not frequent that we calculate experimental or empirical probabilities, but they're actually a little more useful to use actual results, but most of what we're going to see is going to be the other type of probability that's going to be theoretical probability, because we just don't always have time to calculate actual results or perform actual experiments, okay? So we're going to base on theory what's going to happen. Now we can only use theoretical probability when the events are equally likely to occur. And the theoretical probability is based off of something that we call the law of large numbers. The law of large numbers, okay? What does that mean? Well, it's like I said a little while ago. Let me go here for a second. If we were rolling a 6-sided die, right? A 6-sided die, then our options are rolling a 1, a 2, a 3, a 4, a 5, or a 6. So let's say I roll 6 times. Am I going to get one of these, 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 and one of these? In theory, if these were all equally likely to occur, yes, but that's not probably going to happen if we only roll 6 times. What the law of large numbers says is the more times we perform the experiment, the closer we will get to the experimental probability. So if I rolled the die, let's say 600 times, and this is not even that large of a number, but if I rolled it 600 times, I am more likely to get closer to having 100 on each of those each of those options. Now, it's still probably not going to be exactly 100 there, but the law of large numbers says if I took this out where I rolled it 6,000 times, then I'm going to get closer to 1,000 for each of them. And if it was 600,000 and so on, the more times the experiment is performed, the closer we're going to get to the theoretical probability, which is the chances of rolling a 1 would be 1 out of 6. The chances of rolling a 2 would be 1 out of 6. The chance of rolling any of these is the same because these events are all equally likely to happen. Okay? So the law of large numbers says if an experiment is performed many times, I'm talking like millions of times, and the events in the experiment were equally likely to occur, then the theoretical probabilities is what would be evident in the results. We would get closer and closer and closer to 1 out of 6 for each of those options. Okay? so the majority of probabilities calculated are theoretical. Again, we don't always have time to perform experiments and look through millions of actual results, so we base on theory if we can, okay? So 6-sided die is rolled once. What's the probability that we land on a 1? Well, in the 6 options, one of the 6 is a 1. What's the probability that we land on a 4? Well, one of the 6 options is a 4. What's the probability that we land on an even? Okay, well, 1, 2, 3, 4, 5, and 6. This one's even, this one's even, this one's even. So 3 out of the 6 are even. Or if we want a half reduced, or 0.5 for the decimal, or 50%. And then not even would be the odds. This one's odd, this one's odd, this one's odd. So the other 3 out of 6, or 1/2. Okay? There's that. How about this one? A class has 15 boys and 16 girls. One student is selected to recite the pledge. One randomly selected student. Each of those students has an equally likely chance of being picked. What's the probability of selecting a boy? So we would say the probability of selecting a boy is, remember, it's how many, I should have said this up here. When we're looking for, the probability of choosing a 1, it's how many 1s are there, right? What's the number of 1s? And then what's the number of options total in the universal set? So there was 1, 1, and 6 options in the universal set, and that's sort of what we went all the way through. I sort of made an assumption that we have done this before, and I'm not sure that you have, so I'm really sorry about that. The same thing is happening here. If I want to know the probability of selecting a boy, I want to know what's the number of boys in the set, and then I want to know what's the number in the universal set, or total. Okay? So how many boys are there? In this case, there are 15 boys. And then how many total students are there? Well, the 15 and the 16 makes 31 altogether, so our probability would be 15 out of 31. And that doesn't reduce, but just so you can see the options, 15 out of 31, again, doesn't reduce, and we can see that when we tap the fraction button. If we're going to make this one a decimal, we're going to go with the squiggly equal, because we'd have to round this off. And let's see, we have, it's 0.48387, and then it just keeps going, right? Now when you do this in your assignment, in your practice, the numerical feature, when I try to have you type in a number answer, it doesn't deal with fractions very well, and so when you're entering a number answer, I'm going to have to ask you to put a decimal or a percent, and you're going to want to be careful with where I specify to round, okay? If I said to round this, let me go here. Let me go back with this, where our decimal is 0.48387, blah, blah, blah. Okay? If I said round this to the 10th place, round to the 10th place, the 10th place is here. So if I want to round to the 10th place, what I have to do is look at the next number. So I have to look at the 8 and decide if that rounds the number up or down. So since 8 is bigger than 5, it would round this up. We would make this a 0.5. Now if I said, 0.5. If I said to round this to the 100th place, the 100th place is here. So I have to look at the next number, which in this case is the 3, and decide if the number that's next is bigger than 5, then we round up. If the number is less than 5, then we keep it. So since this is less than 5, this stays an 8. So this would stay at 0.48. If I said around to the thousandths, okay, the thousandths place is here, which means I'd have to look at the next number. Okay, now the next number is an 8. Since it's bigger than 5, that tells me to round this guy up. So we would make this 0.48, and then the 3 would go up to a 4. Okay, so I don't know how long it's been since you've rounded, but 10th place, is the first one. You got to look at the next number. Do you round up or do you keep it? Hundredths place is 2 digits after the decimal. You got to look at the next number. Do you round up or do you keep it? Thousands place is 3 numbers after the decimal. Do you round up? Do you keep it? Now, if I tell you to take your or type your answer in as a percent, then after you get your decimal, these would be the percents over here. After you get your decimal, then round it. So if I say to give your answer as a percent, then you don't actually have to do any of this rounding. So as a percent, we go straight to, let me change colors again, straight to what we have up here. This would be, if I multiplied by 100, this would be 48.387 blah 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 percent. Okay. Now, usually when I ask for a percent, I'm going to say round to the nearest whole percent. So then, if I want to round to the nearest whole, that's the ones place here. I look at the next number. Since this is a 3, this is going to stay. So this would be 48% if I was rounding that way. Okay, so I know there's a side lesson there, but I just want you to be able to enter things correctly when you do your practice. Okay, so we're going to say this is approximately 0.48 or 48%. Any of those answers would be fine. In fact, again, I'm really totally fine with just the fraction, but when you get to your practice, you're going to have to be able to input multiple formats. Okay. Alright, let's try the next one. We have a spinner that is spun once. It says find the probability of landing on a vowel. Vowels are A, E, I, O, and U. Sometimes Y, but not this time. So how many vowels do we have? Let's see. One here. I'm going to use my highlighter. A is a vowel, E is a vowel, I is a vowel. That would be 3 vowels out of, that was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options total. So 3 out of 10 is the probability of landing on a vowel. And that doesn't reduce, but 3 out of 10 or 0.3 or 30% would all be fine. Okay, a consonant is not a vowel. Consonants are what we call the rest of the letters. So if 3 out of 10 are vowels, then the other 7 out of 10 are the consonants. Those are the ones that are not vowels. How about a capital letter? Well, all the letters in the spinner are capital, so all 10 out of 10 or 1 or 100% of the time you're going to land on a capital letter. Lowercase letter, none of them are lowercase, so 0 out of the 10 or 0% chance of that happening. How about we land on an A? I only see 1 out of the 10 options that are A's. So 1 out of 10 or 0.10 or 10%. And so if 1 out of 10 times we land on an A, then the other 9 out of 10 times we don't get an A. All right? Hopefully we're feeling okay with this. Now, this last one, what we're looking at is a standard deck of playing cards. And if you didn't get a chance, right before the notes for this particular topic, I posted a picture of a standard deck of playing cards. 52 cards in the deck, where half are red, half are black. If you're not familiar with what a deck of cards looks like, you're going to want to familiarize yourself with the deck of cards. So that picture is available for you. You can download one and print if you want. I did try to input it as often as possible into the practice as well, so that you don't have to keep flipping back and forth for reference. But hopefully you have some concept of what the 52 cards in the deck look like. So we're going to pick one card randomly from this standard 52 card deck, which means there's 52 cards. That's the bottom of the fraction every single time. Okay. Now, the first probability we're trying to calculate is what's the probability of landing on it, or of picking a 2. Of the 52 cards, right, that's got to be our universal set, how many of them are 2s? Well, we've got a 2 of hearts, a 2 of diamonds, 2 of clubs, 2 of spades. 4 of them are 2s. So 4 out of 52, or 4 out of 52 reduces to, I don't want that decimal because I don't want to have to round it. I'm going to make 1/13 my reduced fraction answer. Okay, now if you wanted the decimal, it's going to be about 0.08-ish or 8%. Okay, how about that it's not a 2? Well, if 4 out of the 52 cards are 2s, that means the other 48 out of 52 aren't. Okay? And if the other one reduced to 1 out of 13, then 12 out of 13 times we should not be getting a 2. And just so you can see that again, 48 out of 52. And where did I come up with 48? 52 cards in the deck. 4 of them were 2s, which means the other 48 are not. So 48 out of 52 is the other 12 out of 13 times. Okay? Alright, how about the probability that we land on a heart? So the cards break into 4 suits. You have hearts, diamonds, clubs, and spades. So 13 of the 52 cards are hearts. And 13 out of 52 reduces to 1 out of 4. And that should make sense because 1 out of 4 suits are hearts. So 1 out of 4. And how about red? What's the probability that we choose a red card? Well, half the cards are red, half the cards are black. 26 out of the 52 cards are red. Again, that is half of them. The other half, then, would not be red. So not red is the other cards, the black cards. 26 out of 52, the other half of them. Okay, face cards. Face cards are the kings, the queens, and the jacks. Okay, those are what we call face cards. And there are 3 of them in each suit for a total of 12 face cards total out of the 52 cards in the deck. And 12 out of 52... I'm just trying to be lazy here. 12 out of 52 reduces to 3 out of 13. 3 out of 13. Number cards, this would be not the king, the queen, or the jack. So the ace, which is considered the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the ace, oops, go to green here. The number cards are the ace through the 10. The ace, again, is considered the 1. So this would be 40 out of 52. And that's going to reduce to 10 out of 13. Right? Because these two are corresponding here. You have face cards and you have number cards. That's all you have. So if 12 of them are face cards, the other 40 are not. They're number cards. If 3 out of 13 are face cards, the other 10 out of 13 are not. They are the number cards. Okay? And then the last one. What's the probability that we choose a black ace? Well, there are 4 aces, but 2 of them are black. The ace of spades and the ace of clubs. So there are 2 black aces out of the 52 cards in the deck, and that's going to reduce to 1 out of 26. Okay? Hopefully that makes a bit of sense, and hopefully you have some experience with probability already. So this is really just supposed to be a basic lesson, and some of the probability we're going to look at is going to get a bit more complicated, but just take it one step at a time. So you have some practice to work on. If you need me, just reach out. I'm here to help.